Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to my series of presentation, and my presentation title is Fundamentals of High Voltage DC Transmission System. My name is John Kweko Amogotu, and I've been a professional electrical engineer for the past 30 years, and I'm based in the United States of America. Now let's talk about the outline of this presentation, and I'll talk about basically what is a high voltage DC transmission system and the applications of high voltage DC transmission. Then I'll present to you a historical overview of high voltage DC installations, basically starting from mercury valves all the way up to thyristor valves, then to IGBT valves. Then I'll show you pictures and information of HVDC installations worldwide at different parts of the world. Then move on to timeline evolution of HVDC, how HVDC started and evolving from mercury valves to thyristor valves to voltage source converters, and now we have modular multi-level converters. Next, I'll talk about advantages and disadvantages of HVDC compared to high voltage AC transmission system. When do you decide to pivot on high voltage DC transmission as compared to high voltage AC transmission? Is because of enormous benefits and attributes that HVDC has over high voltage AC transmission. And that is based on the break-even distance. We'll talk about the break-even distance for underground and transmission, and basically subsea transmission, then also transmission line level. Then we'll talk about the different configuration of high voltage DC that we have. Next, we'll talk about high voltage DC transmission, the technology types that we have. Then as you know, the technology types that we have is the current source based line commutator converters, and also voltage source converters. So we'll talk about a comparison between the current source converters and voltage source converters. And in between that, there's something they call capacitor commutated converters. Okay, so that one was introduced to mitigate the drawback of current source converters, LCC type. Next, as part of the voltage source converter technology families, we have different technology types, and that is the half-bridge submodule and the full-bridge submodule. And those are the most prominent ones that are in installation now. Some of them are being planned, especially the full-bridge submodule. And we also have the hybrid submodule, which is a combination of the half-bridge and the full-bridge. Basically, that was introduced to leverage the advantages of both technologies and also mitigate the drawbacks of both technologies. Then we'll move on to talk about the components of voltage source converters, high voltage DC transmission system. Next, we'll talk about the control scheme that is utilized in voltage source converters. And as you know, both technology types, both the current source converters, line commutated converters, and voltage source converters all have the control schemes and different control schemes. Then we'll talk about the fault characteristics, basically that is exhibited by voltage source converters when it is utilized in an MMC configuration, that is a modular multi-level converters. And the application is typically, when it is integrated to offshore wind farms. Next, we'll talk about what is high voltage DC transmission, and that is we'll delve much into what the definition is. And high voltage DC is basically can be defined as a point-to-point, and sometimes you can have a multi-terminal DC configuration and also DC grade transmission level. So it's based on evolution from point to point. And from point to point, multiple point to point, you can achieve a multi-terminal DC. Then multiple multi-terminal DC, you can achieve a DC grid. And from a DC grid, you can achieve the super DC grid. Okay, so that is the goal in the year 2015, is to achieve the super grid, and basically that will integrate transmission between many continents. And it utilizes converters, and these converters, we have the rectifier that basically rectifies the AC voltage to DC, and the DC is transmitted to the inverter, and the inverter also converts the DC voltage, DC power to AC equivalent. And it can also be integrated to a DC to DC converter. And what does the DC to DC converter does? What does it do? Basically it acts as a step up or step down transformer. Basically you can utilize it to either step up the DC voltage or step it down to whatever desirable voltage that you need. And the goal is basically to achieve a multi-terminal DC grid and also a DC grid. Comparably to high voltage AC transmission system, it's known to be highly efficient, especially when you're transmitting larger amount of power and electricity over very long distances. And this is what is utilized in far Southeast Asia, China, and where the hydro power plants are located in the northeast area of China, and the load centers are located in the south area. So looking at distances of about 4,000 kilometers to about 6,000 kilometers, definitely, you need a high voltage DC transmission system, and high voltage AC transmission system is just not going to work. Okay, so looking at this picture below, as you can see over here, we have an AC network and an AC network, a second AC source over here, right? Okay, so connected to this AC network, you have a rectifier, and like I made mention, what the rectifier does is basically it converts the AC power and the AC current to a DC equivalent. And this is the DC transmission line or DC transmission cable. And on this end is the inverter. Basically, the function of an inverter is basically to invert the AC power, AC signal, to invert the DC signal to an AC equivalent, and integrate it to the second AC network. Next, we'll talk about application of high voltage DC transmission system. In the previous slide, we talked about what the definition, what actually is a high voltage DC transmission system. But on this slide, we'll talk about its application. As much as it has enormous benefits and attributes, definitely there should be applications of this technology that basically merits its choice over high voltage AC transmission system. So it is integrated to wind farms, and basically, as you know, that these wind farms are located at a very far remote location, especially the offshore wind farm. And the goal is basically to achieve a higher acreage of wind farms and larger capacity of wind farms. As such, they are located very remote, and basically, it is transmitted by DC to the city center, which may be located many kilometers, hundreds, 200s, 300s, and thousands of kilometers to the load center. It can also be applied in an island power generation, where you have an embedded generation. Embedded generation means that hybrid generation of many generation sources, and that is solar farm, wind farm, and you can have diesel generators, and also a battery energy storage system. As such, basically what it's doing is, when you have a power generation that is in an island configuration, what it's doing is providing power locally to a local load, and it is not connected to the grid. Next, it can be integrated, or it can be applied in a multi-terminal DC configuration. Multi-terminal DC configuration, what do you mean by here? This terminology, it means that if you have more than two converters, basically they form a multi-terminal DC configuration. And Currently, we have a 3 terminal, we have a 4 terminal, we have a 5 terminal, and there are plans to achieve a 6 or 7 terminal. And basically, this is the platform or the basis to achieve a DC grid. Next is a DC grid. From a multi-terminal DC grid, which basically can be achieved in, for example, you're talking about UK, and you can achieve a multi-terminal DC grid based on integration of many converters. And to achieve a DC grid, you can have a multi-terminal DC grid in UK, and you can have a multi-terminal DC grid in, let's say, Germany. So to integrate this multi-terminal DC grid in both countries, basically what it can form a DC grid. So many multi-terminal DC grids basically integrated together form a DC grid. Next is it can be used as a city infill. And what does that mean? As you know, if you have a city which is basically choked with a population, space is just a premium. It's very difficult to build power plants. And as you know, most of the power plants are located very farthest, remote locations. If you ever find a power plant that is located, within the confines or within the boundaries of the city, it means that it was built many, more than 60, 70 years ago or 80 years ago, and it is still functioning. As such, because of space, and also, environmental concerns, in terms of noise emission, it is much better to basically utilize high voltage DC transmission technology, that is especially the voltage source converters, that has the ability to synthesize its own voltage and produce power. And this phenomenon is called a black start. It has the ability to provide power when basically, you don't have any reliable source of power. Next, moving large amounts of power over long distances, and in between transmission corridors, and we'll basically talk about each piece of this beverage. Moving large amount of power over long distance, like I made mention that this is utilized in many parts of China, where basically large amount of power is moved from the northeast area to the south. The load centers, where much of the city centers are located in the south area. And the hydro plants are located like 4,000, 5,000, 6,000 kilometers in the northeast, in the northwest area of China. So HVDC becomes the best option. And in between transmission corridors, let's say you have a 50 hertz transmission, a 60 hertz transmission. Brazil utilizes a 60 hertz transmission, and Argentina utilizes a 50 hertz transmission. Okay. So to basically import and export power between both countries, that can be achieved by HVDC in a back-to-back configuration, which basically, it's called a frequency transformation. Next, we'll talk about historical overview of AC/DC. So this basically is the war between Thomas Edison and George Washington. George Washington was basically vouching for AC, and Thomas Edison was vouching for DC transmission. And basically, at that time we'll see who won, and now who is winning. So DC transmission started, and basically was utilized many in the 1800s, and basically it was used in generation, transmission, and distribution. But it was used at one particular voltage level. You cannot basically, you don't have the flexibility or the latitude basically to step it up or step it down to different voltages using a DC to DC converter. As the years progresses, in getting to the late 1800s, especially in 1880s, as electrical transmission distance increased, especially to the load centers, it just became uneconomical, to transmit power utilizing DC. As such, AC transmission started gaining momentum, and basically Westinghouse basically was the one that started winning this point. So in 1870, the first AC power transformer was built, and the reason being that it was possible because for the power transformer, it gives the flexibility to basically step up or step down voltages. As such, different voltage levels can be synthesized and be used for transmission and distribution level. So this was the time that AC power transmission started gaining momentum and started gaining, great momentum over DC transmission system. Then in 1891, George Westinghouse built the first alternative current distribution system. Then in 1893, that was when basically AC transmission was achieved from the Niagara area, but the frequency that was utilized was 25 hertz, as compared these days we have 50 hertz and 60 hertz. And the reason being that 25 hertz, that is when basically economy comes into play. Everything is reduced, and cost also comes into play. Cost is minimized. So basically, the adversaries war between George Westinghouse and Thomas Edison. So basically, George Westinghouse started winning over Thomas Edison. But later on, it was DC transmissions that will start gaining momentum over AC. So that is when Thomas Edison also started gaining momentum and popularity over George Westinghouse. Okay, so next I'll talk about pictures and information of typical HVDC installations that we have. As you can see, in 1961, the first cross-channel link between England to France, and this was rated as 160 megawatts at 100 kilovolts DC. So that was between the English and the French boundary for a distance of 52 kilometers. Next is another installation, and basically another great picture. And basically this shows the first voltage source converter that was installed in Gotland, Sweden. And that was 50 megawatts, and the voltage level was 80 kilovolts, and that was installed in 1990. So that was when voltage source converter technology emerged as a way of mitigating the drawbacks that was experienced by the current source converters, that is line commutated converters. Then in 1986, a second cross-channel link was also installed, and this was basically bipole, and basically 2 times 270 kV DC, and that has been the largest power cable link. Then also, this also, the Transbay cable, and this was also installed. So this one is a typical of city infill. As you know, San Francisco area in California, and also Pittsburgh area in California, it's a highly densely populated area, and very difficult to install a power plant in that area. So as such, HVDC voltage source converter became the choice to a multi-level system, modular multi-level system. Converter system became a choice for them to install to be able to synthesize its own voltage and transmit power to the city. Next slide, we'll talk about timeline for the evolution of high voltage DC transmission system. So on the left side of right below the year 1999, as you can see, the technology that was only available was current source HVDC, converter HVDC, and that is a line commutated converters. Okay, in between that, there was something they call capacitor commutated converters, CCC. Okay, so that, remember I made mention that was introduced to mitigate some of the drawbacks of current source converters like LCC, because the capacitor commutated converters basically provides the reactive power. Remember I made mention that current source converter LCC requires about 60% reactive power. So as such, capacitor commutated converters was introduced basically to provide that amount of power, which basically prevents you from installing filters in reactive compensation which basically introduced a larger cost. So capacitor commutator converters was introduced basically to cut down the cost that was associated with LCC transmission technology. So in 1954, the first HVDC transmission went into commercial operation, and this utilizes a mercury valve technology. Then in 1965, another mercury valve technology was installed in New Zealand. Then in 1972, the first thyristor valve was installed in that is the Nelson River. I think that's quite close to the New England area and Canada. Then in 1980, that was when somewhere between 1979 and 1980, that was when microcomputer control was introduced to be able to control the equipment that is associated with high voltage DC transmission system. Then in 1984, that was when 600 kV DC transmission level voltage was achieved. So all those installations that were over here, their voltages were below 600 kV. So that was a great achievement in 1984. Then in 1999, that was when voltage source converter, started gaining momentum, and that was introduced to mitigate the drawback that is associated with line commutated converters, that is current source converters. And the first installation was achieved in Gotland, Sweden. Then in 2000, the first installation was also installed in Australia. And in 2010, that was when the first multi-level voltage source converter transmission system was installed. So these installations were much more of a two-level, three-level, the traditional voltage source converters. But in 2010, that was when research and technology basically paved the way for them to achieve an MMC converter, which has much better attributes compared to the two-level and the three-level. Then in 2015, that was when a voltage level of plus or minus 320 kV voltage source converter transmission system was also achieved. Then in 2019 to 2020, that was when the first plus or minus 1100 kV line commutated converter utilizing thyristor technology was also achieved. So that was a great achievement. Actually, this was the Three Gorges River in China, basically transmitting distances of close to about 4,000 kilometers. Next slide, we'll talk about the advantages and disadvantages, when you compare high voltage DC transmission system to high voltage AC transmission system, and why the choice. When do you make a choice, utilizing high voltage DC transmission system? Okay, so for high voltage DC transmission system, you don't have any reactive power loss, and basically, the frequency is 0. So 2 pi FL is 0. So reactive power losses is 0. It's mainly resistive losses that we have in HVDC, and but in fact, the resistance is so low that the resistive losses are even minimal. So as such, since we have reactive power losses, low reactive power losses, and also the resistive losses are low because the resistance is very low, you achieve a lower transmission losses. Also, lower transmission cost and fewer conductors. As you can see, for DC transmission, you only have 2 conductors, and you can have, let's say, for the positive and the negative pole, you can have more than 1 conductor, if you have to bundle the conductor. But you have a lower transmission cost in terms of terminal cost. Initial terminal cost, let's say, can be a little bit higher, but basically, with time, it's basically becomes lower as the transmission distance increase. You can also have the ability and capability to synchronize 2 AC networks that have different frequency. And I made mention of it, you can utilize it for Argentina, and that is what is utilized in Argentina and Brazil. Argentina has 50 Hz transmission network, and Brazil has a 60 Hz transmission network. So how do we import and export power or interconnect transmission network between both countries? We have to use HVDC in a back-to-back configuration. Basically, that helps with frequency transmission and frequency conversion. We can also achieve longer lengths of underground and submarine cable. And like I made mention that we have a break-even distance for HVAC transmission. For underground cable, the break-even distance is between 50 kilometers to 80 kilometers, and that is based on the amount of power that is being transmitted. And especially for a 200 megawatts, that is the break-even distance that you want to basically utilize HVDC. So greater than that, you can achieve a longer length of underground and submarine cable, greater distances, more than 80 kilometers. We don't have charging currents. As you know, for high voltage AC transmission system, there's something they call charging currents. And for HVAC cables, underground cables, because of the high capacitance, and the capacitance is even higher for submarine cable because of a lot of insulation components. So you can have high charging currents. But for DC cable, we don't have that high charging currents, which will require another reactive power to charge the current before you can be able to transmit power through the cable. And for transmission conductors, right, there's something they call straight capacitance, right? They are very invisible. You have a straight capacitance that basically, forms an invisible capacitance from the conductor to ground, and in AC transmission, you need to charge that straight capacitance. So that itself requires a higher amount of charging current and charging reactive power to charge that capacitance. You don't have a stability problem, as you know, in HVAC transmission system, when there's perturbation in the AC grid, you can have a stability problem because of if you don't have reactive power to basically provide reactive power to restore voltages, you can have. But with HVDC, you can have a bidirectional of flow of power, and also the converters have the capability to basically provide reactive power to support the grid, and also to prevent the rate of change of frequency. Next, no skin effect, and skin effect is basically prevalent in high voltage AC transmission, and that is based on the frequency where the current is not flowing through the peripheral of the current. The current flows through the peripheral of the conductor, the surface area of the conductor, and it doesn't flow through the whole cross-sectional area of the conductors. There's also something they call Ferranti effect. You don't have that phenomenon in HVDC. Ferranti effect basically occurs when you have an HVAC transmission line that is connected to a light load or not connected to a load, where you can have a very high voltage at the load end. You wouldn't have that phenomenon in high voltage DC. Next, spacing and footprint. HVDC requires less space. As you can see the picture from the right, you have a look at the picture of the tower structure compared to the tower structure for an HVAC. This is a tower structure for HVDC. So as you can see, right away it's very small, and also the tower structure is also very small. So as such, it has less spacing and footprint. And also for AC transmission system, since you require reactive power compensation at various distances, at let's say for transmission level, you require for every 450 to 500 kilometers, you require reactive power compensation. Basically, that introduces that you need to install capacitors and start point and static power compensators. Basically, that itself introduces much more footprints and basically much more spacing. Also, you have less corona. Corona is much prevalent in HVAC transmission, where you have basically much electric field, higher electric field, basically that breaks the air around the conductor, and that can have an effect on the insulators, basically that is holding the conductor. And it can also cause an interference of communication that is close by to the transmission system. You wouldn't have such a phenomenon in HVDC. Also, for HVDC, you wouldn't have a reactive compensation. Remember I made mention that for HVAC you require reactive power compensation, which basically requires installation of capacitors, at distances of 450 kilometers. So for a distance of 1,000 kilometers, basically for every 450 kilometers, you require reactive power compensation, and that requires you to basically build a substation, that can have this reactive power compensation. Basically, HVDC is provides more stability, more reliability, and basically the ability to basically achieve a power reversal. You can achieve a power reversal in line commutator converters or current source converters by basically swapping the polarity of the cables. You can also achieve power reversal easily, in a voltage source converters by basically through controls by basically achieving swapping, changing the polarity of the current. Now let's talk about the disadvantages. As much as we've talked about the advantages, and the choice for HVDC over HVAC, let's talk about the disadvantages. The terminal cost can be very high, though as you increase the distance, basically right beyond the break-even distance, basically it basically pays off. The terminal cost becomes lower. So for underground cable or submarine cable at distances more than 80 kilometers, basically the terminal cost becomes much lower. But distances before 80 kilometers, you have a high terminal cost. And also, as part of the terminal cost, right of way, for HVDC is much lower, and the tower structure is also has a much lower cost comparably to HVAC. When you operate a HVDC transmission network and its component, especially the power electronics, right, it introduces harmonics. So basically, you have to install filters, to filter out these harmonics, because the introduction of these harmonics, if these harmonics basically feeds into the AC network, basically it can cause problems. It basically can cause problems for the protected relays, and it can also cause problems for transformers. It can cause heating for the transformers. It can also cause heating for rotating machines that are basically on the roadside of this transmission network. HVDC has a limited overload capability. Matter of fact, the voltage source converters do not have overload capability at all. It's the line commutator converters that have a little bit of overload capability, about 115 to 125% of overload capability. It also requires a significant reactive power requirements, and this basically pertains, this applies to line commutator converters or current source converters. Like I told you, I made mention that it requires about 60% of the rated power. That's the reactive power requirement of that is required by these current source valves. So basically you have to spend that amount of money to basically build filters, and also install capacitors or startups or static power compensators to provide this reactive power requirement. Next, we'll talk about commutation failures. And when you have a line commutator converters, you have a rectifier and you have an inverter. Especially when you have a disturbance on the AC grid side that is integrated to the inverter, which basically it can lead to a commutation failure, and basically you have to basically de-energize this HVDC transmission system and basically resolve the problem of commutation failure. Next, line commutator converters or current source converters requires a strong voltage source or AC grid. And what does that mean? A strong AC voltage means that the AC grid has to be very strong, or has to be stiff, has to have a stiff voltage, which means that it should have a very high short circuit ratio, high short circuit contribution from all the generators that are tied to this AC network. As such, when there's a fault, right, it doesn't allow the voltage to change. The voltage change is just minimal. So that is what we mean by a strong source or a strong voltage source or a strong AC grade or a stiff AC grade. So current source converters are, because of commutation failures and all those problems that is associated with this thyristor-based technology, it requires a strong voltage source before it can function correctly. Okay, so next we'll talk about the optimal choice. When do we decide on high voltage DC transmission system as compared to high voltage AC transmission system? As you can see over here, I have a chart. Basically, on the vertical axis, we have cost of the scheme, cost of HVDC scheme, and cost of DC scheme. And on the horizontal axis is a transmission distance. So on this chart, we'll see the break-even distance when we decide on implementing HVDC technology as comparable to HVAC technology. When we are utilizing an overhead line transmission system, and when we are utilizing an underground cable or a submarine cable. As you can see on the vertical axis, right, we have costs. So for a DC converter station for HVDC transmission scheme, we have a higher terminal cost. And what is the reason? It's because the components of an HVDC transmission scheme have a higher cost. Especially the converters, they have a much higher cost compared to the AC station. But what is the caveat? The caveat is that HVDC and DC converter station has a much lower right-of-way cost for the transmission tower, and also the tower cost is much lower if you compare it with AC transmission substation. And also, DC transmission system utilizes fewer conductors compared to AC transmission network. AC transmission network utilizes 3 conductors as compared to DC transmission system that utilizes 2 conductors. So the caveat is these 3 attributes basically have a much lower cost, though the terminal cost is much higher. So now let's talk about the break-even distance. So for an overhead transmission line, right, at distances of 800 kilometers down the transmission line, right, that is when you decide for distances greater than that. That is when you can decide to implement a high voltage DC transmission technology instead of a high voltage AC. It becomes much cost effective. As you can see over here, the blue curve is below the red curve. The red curve is for AC transmission, and the blue curve is for DC transmission. Below that, AC transmission has much more benefits than DC transmission system. Now let's talk about our submarine cable at distances between 50 kilometers to 80 kilometers, right? Below that, that is when you can utilize a high voltage AC transmission system. But at distances greater than 50 kilometers to 80 kilometers, then you want to decide on HVDC transmission system. Especially, when you tie it with load. That is, if you have a load of 200 megawatts, you are transmitting an amount of power of 200 megawatts and above, then you want to consider utilizing HVDC transmission system. Similarly, for underground cable, for distances greater than 80 kilometers, and with a transmission load of 200 megawatts, you want to decide on high voltage DC transmission system. Next, we'll talk about the types of high voltage DC configurations that we have. First, we'll talk about symmetrical monopole configuration. And what is a symmetric monopole configuration? As you can see over here, this is a symmetric monopole configuration. We have a positive pole and a negative pole. The reason why we utilize the word symmetric monopole is because both poles are similar, have the same rating. So if it's a plus or minus 320 kV, the positive pole is rated at 320 kV and the negative pole is rated at 320 kV. So it has two converters. One converter acting as a rectifier that rectifies the AC voltage to a DC voltage equivalent, and another converter acting as an inverter that inverts the voltage from DC voltage to an AC voltage equivalent before it is integrated to the grid. Next is asymmetric monopole. For asymmetric monopole, the poles are not similar, right? So you can have a positive pole or a negative pole, and the most popular one that is utilized is a negative pole, right? Because of the negative pole basically requires less insulation, and less insulation basically translates into less cost. And the return can be a ground return. So for the ground return, you can utilize the seabed as a return, or you can use the metallic return. And this if you use a metallic return, basically the voltage rating is much lower, right? Basically, yeah. So for an asymmetric monopole, basically the cost to implement that is much lower compared to a symmetric monopole. And I will talk about the reliability part in the next slide. Next is the bipolar configuration. For the bipolar configuration, basically it has 4 converters, right? So you have one pole that is rated at a positive, and then another pole that is negative. And basically in between that is the neutral, and the neutral is grounded. On this side, you have the AC converters, and on this side you have the AC converters. Basically, the goal of these converters is to basically step up or step down the voltage. For this side, you want to step up the voltage to a higher voltage to be able to achieve the DC voltage equivalent. Next is back-to-back. Back-to-back, like I mentioned, both converters are located in the same vicinity or the same substation. There's no transmission network connected between both converters. And that is what is utilized to synthesize or integrate different countries that have different frequencies of transmission. That is, if a country has 50 hertz and another country has 60 hertz. And I made mention of that in the earlier slides. That is what is used to integrate transmission network between Argentina and Brazil. Next is a multi-terminal DC transmission network, and basically I'll show you a picture of it in the next slide. That is when you have more than 2 converter terminals. That is when you have 3 converter terminals, 4 converter terminals, 5 converter terminals, 6 converter terminals. Next is a rigid pole. And for multi-terminal DC converters configuration, HVDC configuration, you can have different configurations. That is a series, parallel, or meshed. Next, we'll talk about the different types of the HVDC configuration. We'll continue talking about that, and we'll talk about the different types of multi-terminal DC grids that we have. Remember, I made mention that for multi-terminal DC grid, HVDC grid configuration, we have the series, and we have the parallel, and we have the mesh. So this is an example of how the mesh look like, right? Okay, so this one is a typical parallel type, right? So this one is much more of a series parallel configuration. So we have a 3-terminal configuration. We have the sending end converter. So this converter is located at an offshore substation platform, and it is integrated to an offshore wind farm at a very remote location, right? So the goal is of this converter is to basically convert the AC power or AC current to a DC equivalent and transmit it through a subsea DC cable to the receiving end converter. So these converters are located at an onshore facility, so or onshore substation, and this is a second receiving converter. This is also located at an onshore substation, right? Okay, so it converts the DC voltage to an AC equivalent, and this is a step-up transformer, a transmission level step-up transformer that steps the voltage from a lower voltage, let's say from 230 kV to a 400 kV to 400 kV transmission level to the AC grid. Next is 1, 2, 3, 4, 5. So this is a 5-terminal multi-terminal DC configuration. So on this side, these are converted. These converters are basically integrated to a wind farm, right? Okay, so You have a wind farm that is integrated to this converter. So you have a step-up transformer that steps the wind farm um, voltage from the AC collection voltage, let's say from 33 kV to a 230 kV transmission level, and or 33 kV to a 230 kV. So you have a 1, 2, 3. So these three converters are basically sending in converters. These are all located at onshore substation. So the goal of these converters is to convert the AC voltage to an equivalent DC voltage before it is integrated to this DC transmission network with a DC bus and DC breakers. So this DC transmission network basically transmits the DC voltage to this onshore substation. So these two converters are located at an onshore substation facility. So its goal is to convert the DC voltage or the DC power to an AC power equivalent. So let's say it converts the DC power, let's say from a plus or minus 320 kV to a 230 kV AC voltage before it is stepped up to a 230 400 kV transmission level voltage to the AC before it is integrated to the AC grid. Next, I've made mention of the different types of HVDC configurations that we have, right? I've talked about symmetric monopole. So let's talk about the pros of the symmetric monopole. So for the symmetric monopole, there's, during operation, you don't have any DC ground current flow unless there's a fault. And also it requires smaller cables, and it can utilize standard AC transformers. And why do we say that? That is why do we say that it is an advantage? When a converter utilizes a converter transform, basically the insulation has to be built to withstand both AC and DC voltage, and its stresses, so that itself introduces a lot of cost to do that. But if it can utilize a standard AC transformer, but that basically can only withstand AC stress, then basically, the cost is much lower. Now let's talk about the cons, the disadvantages. It doesn't have the symmetric monopole doesn't have any redundancy. So when there's a fault on either the positive or the negative pole, basically, there's no redundancy. Basically you cannot transmit power. So basically you have to shut down the HVDC configuration and implement the repair before you can restart it. Also, because it requires full rated cable. Remember I made mention that especially for the symmetric monopole, you require poles that are rated at plus or minus 320 kV. So basically it requires additional costs and increased costs. Except for the asymmetric pole, that basically for the positive or the negative pole, you can have a full rated cable. But for the return, which can basically be done through the subsea, or then you have a ground return, then or metallic return, then you don't have to utilize a full rated cable, and basically the cost can be very low. Also, you can have a higher power losses, especially with a symmetric monopole, because you are utilizing full rated cables when compared to the asymmetric monopole, because you are utilizing only one full rated pole, and the return is either through the ground or through the seabed, or you can utilize a metallic return. The asymmetric monopole, like I indicated, that it can have a lower cost compared to the bipole or the symmetric monopole, because it's utilizing only one pole, which is either a positive or negative pole, and the return can either be through the ground or the seabed or a metallic return. As such, because during standard steady state operation, there is no DC ground current, and the ground return can have a lower matching voltage compared to the operating pole, that is the positive or the negative pole. And the disadvantage is that there's no inherent redundancy. Now let's talk about the bipole. So it has 4 converters, right? The middle part is the neutral part, which is grounded at each end, right? So during steady state operations, you don't have any DC ground current flow, unless of course there's a fault. And even then, the fault, the converters control the fault. It has an inherent redundancy. That is, if there's a fault on one pole, you can then operate it, shift from a bipole configuration to a symmetric monopole configuration, and utilize basically one pole and the neutral as a retain. It has a double capacity, because it has a four converters, and basically when one pole is out, you can utilize the other pole, compared to the symmetric monopole configuration. The cost, of course, can be high because you have four converters in place. Next is the rigid bipole, and I think I showed you a picture of it basically. And this is quite similar to the bipole, but it just utilizes switches on the DC transmission cable, and you can have these switches located in the switchyard. It doesn't have a DC ground current flow during steady state operation. And you don't need a metallic retain or electrodes, as you use it in an asymmetric monopole, where you can utilize a metallic retain or electrode utilizing the seabed or the underground or the ground. It also has an inherent redundancy in it. Like I made mention that it has a positive or negative pole. So when one pole is out, that is when the switching takes place. Basically, the switching is done to basically, remove, the converter, the faulted converter. It also has a double capacity, just quite, similar to the bipole configuration. And basically, the drawback or the disadvantage is that it requires high-speed switches that are located in the AC switchyard. Basically, that is able to switch out the faulted converter and basically implement, get back the converters that are not faulted. Next, we'll talk about the HVDC technology types that we have. Remember, I made mention that we have two main technologies. That is the current source converters, also known as line commutator converters. Okay, so this technology is a very mature technology and has been around for a long time, and since the 1950s, and basically this was introduced, thyristor base was introduced to mitigate the drawbacks that was associated with a mercury valve type of HVDC technology. It's thyristor based, and basically, that is more current source control. It is also referred to as classical type or conventional based type technology. So if you hear those buzzwords, classical, conventional, it's all referring to the current source converter or line commutator converters or thyristor based converters. It has a much lower converter power losses, as compared to voltage source converters. I think the losses per converter is about 0.5%, as compared to voltage source converters that is about 1.5%. I mean, you can, on the other hand, you can achieve a much lower power losses, if you move, into the MMC converters, voltage source converters, and that has a power loss of about 0.8%. And also, it has a high transmission power capability. As you can see, comparing the line commutator converters to the voltage source converters, for the line commutator converters or the current source converters, you can achieve a voltage level of a plus or minus 1,100 kilovolts, and also 10 gigawatts of transmission. Compared to the voltage source converters, where the power transmission is limited by the voltage of the cable. The highest voltage that has been achieved, that is being led to commercial operation, is plus or minus 520 kilovolts for the voltage source converters, as compared to the line commutator converters, where you can achieve a DC transmission voltage of a plus or minus 1100 kV. An inductor is used on the DC side, and this is a large mass of inductor, and its goal is to basically keep the current stiff, and also to limit, when there's a fault on the DC side, to limit the rate of rise of the DC current. And also, constant current, and constant current is achieved, utilizing the inductor on the DC side. It is more tolerant to faults, and what does that mean? When we say that line commutator converters are very tolerant to fault, it means that it has the ability to control through thyristor control. You can control the thyristor by changing the firing angle of the thyristors to be able to control the fault. You can also utilize the large size inductor to basically limit the fault. Next, has a larger footprint, and basically it requires a larger space, and it can be more expensive because of much auxiliary equipment that is required. And what are the auxiliary equipment that is required? That is filters, right? Remember, I indicated that it generates a lot of harmonics, and basically it requires a lot much more of filters to be installed. And also, because of the larger reactive power requirement, basically you have to install capacitors, and also if you don't install capacitors, you can install STATCOM, static synchronous compensators, or static var compensators as a means of providing reactive compensation. It also requires a strong grid, that means that the grid has a high short circuit ratio, or a stiff grid. And I indicated, I think I made mention that, reactive power compensation, which has to be provided by capacitors and filters. I think the highest configuration that we have for the current source converters is plus or minus 1100 kV, and that is 10 gigawatts megawatts. That's a huge power transmission. That is being transmitted over distances of greater than 4,000 to 6,000 kilometers, and this is based in China. And that is what I indicated, that is utilized to transmit power from the hydro facilities that are located in the northeast area of China, all the way to the southern area of China, where the city centers, where the load centers are located. One of the drawbacks is it cannot operate below 10% of its rating. So 90% of power, basically, that's a limitation with the current source converters. Next, voltage source converters. And we'll talk about this technology. It is an IGBT based. It utilizes insulated gate bipolar transistors as compared to current source converters that utilize thyristor based. It's self-commutating. What does it mean? You can also say that force commutating. It generates its own voltage. It synthesizes its own voltage. As such, it can be utilized for black starting. That is providing a voltage when you don't have any power. It utilizes a capacitor on the DC side, and especially for the 2-level and the 3-level, it utilizes a large capacitor. But for the modular multi-level converters that has a lot of sub-modules, the capacitors are basically distributed, so the capacitors are very small in nature as compared to the traditional 2-level and the 3-level. So it's utilizing capacitors as compared to the current source converters that utilizes inductors on the DC side. So, utilizing capacitor, what does it do? It stores charges. It gets charged and it stores charges to maintain a constant DC voltage on the DC link. Like I made mention, because of its inherent self-commutating capability, right? Forced commutation capability, it has the ability to provide black start and basically provide a voltage to when there's no power or no voltage. It's less tolerant to faults. Remember, I made mention that current source converters are more tolerant to faults because of the presence of large inductors, basically that mitigates the fault current, and also the ability to control the thyristors. For voltage source converters, they are much more vulnerable to faults, because unless of course you are utilizing the full bridge sub-module MMC. But for the half-bridge sub-module MMC and the 2-level and the 3-level, you don't have any fault control capability in it. So as such, when the fault occurs, it becomes very difficult to interrupt the fault. Also, it is smaller. It has a much smaller footprint. And what does that mean? That means that as you compare it to the current source converters, you don't require reactive power. You don't require capacitors. And matter of fact, it's only the 2-level and the 3-level that requires filters because of the harmonics that is generated. But for the half-bridge sub-module and the full-bridge sub-module, that is modular multi-level converters, you don't require filters. As such, it has a much smaller footprint. It has What's a higher converter switching loss? Remember, I made mention that the switching loss for voltage source converter, especially the 2-level and the 3-level, it's operating at 1 to 2 kilohertz switching. So that of frequency, switching, that is translate into much of conduction and switching loss. It is only when you move to the MMC technology, voltage source converter technology, that is when the converter switching loss is about 0.8%, because the frequency of switching is much lower, because you are utilizing basically 150 hertz, 200 hertz to switch the converter. So that itself translates into a much lower switching loss. Next, we'll move to the types of voltage source converters. And remember, I made mention that the traditional level of the traditional types of voltage source converters that we have is the 2-level and the 3-level. And I'll show you a picture of how the 2-level look like. And we also have a multi-level converters. So the 2-level and the 3-level and the multi-level converters are mostly utilized in a much lower voltage, in medium voltage distribution. And especially the wind turbines, they mostly utilize the 2-level converters. That is what is located in the wind turbines. And for variable speed drives, basically they utilize multi-level converters. That is the H-bridge and the cascaded H-bridge as well. So for the multi-level converters, right, basically your rate of change of voltage with time, because the voltage is distributed, across the many modules, basically it results in much stress on these converters. And also because the switching and conduction losses are much lower because of the lower switching frequency. And also, harmonic distortion is much reduced because of the lower switching. And also utilizing several modules, which basically, you can build it to the desired voltage that you require. And as you build it more and more to achieve the desired voltage, you achieve the perfect sinusoidal voltage. So basically your harmonic distortion is very reduced, and basically you don't require voltage for that. On the other hand, the disadvantage is that it has a much complex control scheme, and investment cost can also be increased, and also it requires additional algorithm, especially for the half bridge and the full bridge sub modules, right? It requires an algorithm to balance the voltages on the capacitor module, and that itself introduces additional cost. So this is a picture of or a schematic of how a single base of a voltage source converter. As you can see over here, right? You have only two IGBTs, T1 and T2, basically. So during its operation, you have the first one is T1 is on. So when IGBT T1 is on, and this one is off. And the next one is when T2 is on and the T1 is off. So this is basically done through pulse width modulation. Okay, so you have the capacitor on the DC link. On this side is the DC link. Okay, so and on this side is the AC, and this is the freewheeling diode. Basically, that is added to protect the IGBT. So this capacitor has been basically broken into two, right? Okay, so you have the top part and you have the bottom part, and basically it's synthesizing two voltages, right? You have a plus VD over 2 and another one that is minus VD over 2. Next, we'll talk about the advantages of the voltage source converter. Okay, so remember I indicated that the voltage source converter basically became the technology of choice over line competitive converters, and basically it allows you to control independently the active and reactive power flow. So you can achieve a bidirectional flow as compared to line commutator converters that has only one direction flow. If you want to reverse the direction of flow, basically you have to shut down the converter and basically reverse or swap the polarity of the cables. And also it doesn't require reactive power compensation because it can synthesize its own voltage. It has a much faster response, so as such, due to the use of IGBT, so it allows faster restoration when basically, you have a blackout. It can also be connected to a weak grid. Remember, I indicated that one of the drawbacks or one of the weaknesses of line commutator converters is when it is connected to a weak grid, then it has a problem of operating reliability. So it always requires a strong grid, a stiff grid, a grid that has a very high short circuit ratio. But voltage source converters can be connected to a weak grid, because of its inherent ability to generate its own voltage. And also it can be integrated and connected to remote offshore wind farm facilities. And much more compact and very smaller footprint. And it can utilize ordinary transformers. Basically, that translates into less cost. And a power reversal can easily be achieved as compared to line commutator converters. And this can be done through the computer, through the controls, by reversing the polarity of the current. It can also provide power to passive network. Let's say if you have a local, this comes into play when you have an island mode of operation. So basically it can provide generate its own power and provide it to the local network. Next, we'll talk about modular multi-level converter. What it is actually, that is the state-of-the-art technology, and technology is moving so fast that basically, we're hoping that the next technology after MMC will come soon. Okay, so let's go through this schematic. All right, right on top of this MMC sub module, right? Basically converter, we have a sub module that consists of many of these sub modules. So it can either be a half modules sub module or a full bridge sub module, right? That are connected in series. You can have hundreds, 200s, 300, thousands of these, right? So you stack up, let's say, thousands of these to achieve whatever desired voltage that you have. And these sub-modules have been daisy-chained. There's something they call daisy-chain. That daisy-chain means that they've been connected in series to achieve the required voltage that you need. So this part of the converter is called an upper arm converter, right? Okay, so this is a typical scheme of a half-bridge sub-module. It has two IGBTs, right? So this is the sub-module capacitor. So this is where it stores all the charges and the voltage to basically operate this sub-module. Then below that is an inductor, right? So the goal of this inductor, or reactor, is basically to control circulating current, and also when there's a fault inside this converter, is to basically limit the fault a little bit and prevent circulation. Okay, so sometimes you can have a differential in voltage, right? Okay, phase A, phase B, phase C, right? And you can have a difference in voltage, and basically this difference in voltage being operated between different legs can lead to circulating current. So the purpose of this inductor is basically to control that circulating current. Below that is, they call it the lower arm. So right on top is the upper arm, and below that is the lower arm. So similarly, this also has series cascaded submodules. It can either have a half bridge submodule or a full bridge submodule. So these are all connected in series. So you have this is a picture of one submodule. So you can have thousands of these, hundreds of these, 200s of these, 300s of these, all connected in series and daisy chained. So similarly, you also have an inductor over here. Remember, I made mention that when these converters are in operation, right, you can have an unbalanced voltage between each leg. Leg 1, leg 2, leg 3, right? You can also have an unbalanced voltage between the upper arm and lower arm, which can result in flow of circulating current. So the goal of this inductor is basically limits that circulating current flow. Next is the phase reactor, right? Okay, so if you want to exchange power with a grid, right, you need a phase reactor. So the converter itself synthesizes its own voltage, AC voltage, right, with a phase angle. Then the AC grid also has its own voltage with a phase angle, right? So the phase angle between the AC grid voltage and the synthesized voltage of the converter allows basically, and the phase reactor allows that uh, uh, exchange of power of active and reactive power with the grid. Next, I will talk about the components of the voltage source converter. Okay, so let's go and take a look at the picture on the right side. You have basically an onshore HVDC substation, right? Okay, so as the AC transmission line comes, we have an AC switchyard right here, as you can see over here. That's a description of the AC switchyard of your AC transmission network that comes into here. So over here you have buses, circuit breakers, disconnect switches. Then part of the AC switchyard, you have shunt capacitors, right? So shunt capacitors, what does it do? Its goal is to basically to provide reactive power compensation. You know, when voltage and to regulate the voltage levels. We also have harmonic filters. Remember, I mentioned that if you have converters, especially the current source converters that are located in this valve hole, when they operate, right, they create harmonics, and these harmonics require a place that they need to flow, and they flow to the grid, AC grid, and where they cause a lot of problems. Especially, they can cause heating in the transformer winding. They can also cause heating in rotating machines, motors, as such. So you need to have a harmonic filter that will filter these harmonics that are generated by these converters that are located in the valve hole. Next is converter transformers. And what is the purpose of these converter transformers? These converter transformers also provide isolation between the AC and the DC side. It also provides the required voltage. It steps up or steps down the required voltage that is required by these converters that are located in this valve hall to achieve the required DC voltage. In the valve hall, we have converters, valve basically thyristors, if it is a thyristor, or IGBT, they are located here, where basically during operation, definitely they generate heat. So it has a cooling medium. And the cooling medium, basically, it can utilize a glycol, or it can utilize deionized water to basically cool these valves when they are in operation. So the AC to DC conversion occurs in this valve hall. So outside is your DC power that is basically fed to your DC line, and on this side is your DC switchyard. Basically, you can have a DC filter here, and you know, you can have other components basically that you can also have the DC capacitors, you know, as well. You know, these are all located. Remember, I indicated that, you know, if you have a DC capacitors, especially for the 2-level and the 3-level, it's a large capacitor that is located here. Next is the deeper schematics, right? That shows, you know, HVDC scheme, right? So on this side is a picture of an AC filter, right? So you can have a double tuned AC filter. You can have, on this side is a singly tuned AC filter. Then on this side is a converter transformer. You know, I've already described what a converter transformer does. On this side is a DC filter. And on this side is a singly tuned DC filter, and on this side is a DC surge capacitor. Basically, its goal is to basically mitigate over voltage and the transients that are associated with that. And on this side is arresters. So all these components are located here, and all these components are located on the AC switchgear, right? So you have the transmission line cables, right? I made mention of it. These are the transmission line cable on the AC side, and on this side, these are the transmission line cables. Okay, so components of a voltage source converter, right? Okay, so a voltage source converter, right? On the DC side, we have a DC cable, right? So this is a typical picture of how a DC cable looks like. Okay, so inside is the core of the DC cable, right? Then this is an AC cable, typical picture of an AC cable, and the fiber optics that is embedded in this cable, right? The fiber optics is usually utilized for communication, communication to a SCADA center or communication between the two relays, right? Okay, so this type of cable is what is used in inter-array. If let's say you have an offshore wind farms, right? Inter-array in between wind turbines, or in between, let's say if you have a radial feed, in between each radial feed, or in between AC collection point to the step-up transformer. This is the type of AC cable that is utilized. Next is a picture of a DC transmission line. Okay, so as you can see over here, there are two positive pole and a negative pole, right? And like I indicated that depending on the DC voltage, right? Let's say you have a plus or minus 1100 kV DC voltage. Definitely, you're gonna have many conductors. You're gonna have let's say 8 conductors, And so as you can see, these conductors are bundled, right? You have 4 conductors that are bundled together, and you have another 4 conductors that are bundled together, right? So this basically helps us to achieve that amount of voltage and also the amount of current that is going to flow based on that voltage, DC voltage level. Next is a converter, a valve. Usually sometimes they utilize the word valve or a converter. So it's all the same thing, So this is a typical IGBT, right? For a plus or minus 320 kV voltage source converter. So the valve hole, this is what is located inside the valve hole. In my previous slide where I made mention of the valve hole just before the DC transmission substation and the DC transmission line. This is what is located inside. So this is where the IGBTs are located, or on this side is a typical thyristor. This is where the thyristors are located, and the cooling system associated with these valves. Next is a capacitor, right, at the substation. So this is a typical capacitor at the AC side. So this is how the capacitor looks like. Next is a nice, beautiful picture of a converter transformer. So this is actually a converter transformer for a converter that was used for the Three Gorges River, basically a hydro transmission system from a Three Gorges River. So basically, it is rated at plus or minus 100 kV DC transmission system. It basically allows you to achieve that amount of DC voltage for DC transmission. So basically, this is based in China, and this was manufactured by Siemens. Actually, the length of this transformer is about 40 to 50 meters. So just imagine half of 100 meters track. So that's how big this transformer looks like. So next is another picture of this transformer. As you can see over here, this is a single phase. Actually, it's a single phase. So just imagine you are utilizing 3 of these. And like I made mention that the length is about half of 100 meters track field. So in the middle of 100 meters, that's how these transformers can measure. So this is the bushings, how it looks like. And because of the high voltage, you utilize a corona ring or graded ring. This helps to basically reduce the stresses that is around the terminal over here. Next is an explanation of our modular multi-level converter, how they look like, right? Okay, so the 2 known configurations that we have, like I made mention that it's a half-bridge submodule and a full-bridge submodule. And we also have a hybrid combination of a half-bridge submodule and a full-bridge submodule, right? Okay, so for the half-bridge submodule, right, basically it has a lower amount of IGBTs. It is utilizing 2 IGBTs compared to a full-bridge submodule that is utilizing 4 IGBTs, right? So that is the difference, right? The half-bridge submodule lacks the ability to be able to control or extinguish a DC fault current, compared to a full bridge that has the ability to basically block or control a DC fault current, right? So when you are utilizing the half-bridge submodule, right, you need a DC breaker, right, because it cannot block a DC fault current. It will allow DC fault current to feed through the freewheeling diode. Whilst full bridge can basically block a DC fault current, right? So when you are utilizing a full bridge submodule in an HVDC configuration, all you need is a high-speed mechanical switch on the DC side. You don't need a DC circuit breaker. On the other hand, if you are utilizing half-bridge submodule as your converter technology, then you need a DC circuit breaker to achieve a selective fault clearing strategy. Like I made mention that the half-bridge submodule utilizes 2 IGBTs. As such, the conduction losses and the power losses are much lower, right, as compared to a full bridge that utilizes 4 IGBTs. Also, you can scale it to whatever voltage. Like I indicated, that many of these submodules are connected in series, cascaded in series, daisy chained in series to achieve the required voltage that is required, or the desired voltage that is needed, and basically it allows you to achieve the perfect sinusoidal waveform. As such, you don't need basically harmonics to basically filter out any distortion. Next is the control scheme for a voltage source converter, right? So basically you have a converter, a voltage source converter over here, and you have a voltage source converter over here. So you can have a wind farm on this side or an AC grid on this side. You can have a wind farm on this side, or you can have an AC grid on this side, right? Okay, so in between this is a DC link, right? Okay, so this basically is a control scheme for a 2-level voltage source converter. Like I indicated, that is how the voltage source converters evolved, right? So these capacitors are very large, bulky capacitors that are located in the DC substations, right? Okay, so on this side, you can choose active and or reactive power control. You have a choice, okay? Or AC voltage control. So let's say on this side, right, we utilize reactive power control and AC voltage control on this side. So that will be our outer or upper layer control, right? So we have a dispatch point that's coming from our dispatcher control center. So basically, they will dispatch the DC voltage point that we need, and the AC, the active power point that we need, right? So based on the DC voltage point that is dispatched and the active power that is dispatched to us, we can calculate our reference point for the quadrature axis current reference point and the direct axis reference point, right? So that will be our reference point for the inner control loops, right? Okay, so on this side, we have an AC voltage control and reactive power control. And like I made mention that we can also have a choice of active power control and AC voltage control, right? Okay, so based on what is measured, right? We are measuring from here. We have a dispatch reference point, right? So what is measured, we are calculating our IQ and our ID, our quadrature axis current and our direct axis current. So we have a reference point of a direct axis current and quadrature axis point, and we have a measured point. So we can calculate our error. So we have a control loop over here, our current control loop, which is a PI control loop, proportional integral control loop. That basically calculates the error between what is dispatched and what is measured. So it drives the error to a 0 and provides calculates the required DC voltage. So this is your direct axis voltage and quadrature axis voltage that is calculated from the error from the quadrature axis current and the direct axis current and provides the firing signal to the converter as well. So the firing signals comes from here, and based on also the measured DC voltage that comes into this. On this side, you can also have a control, another control. You can have a DC voltage control. You can have active power control with AC voltage control, or you can have a reactive power control with AC voltage control. You can have a DC voltage control with an AC voltage control, right? Okay, so similarly, you have a reference point of a that is dispatched. That is a DC voltage reference point, active power reference point, reactive power reference point. So based on that, the direct axis reference point, current reference point is calculated. Quadrature axis reference point is calculated. Then here is your measured active and reactive power point and measured DC power point. So from there, it calculates your ID current and your quadrature current. Then basically it compares with the reference point and basically calculates the error. And this PI control drives the error to a minimal level. Then from there, basically it calculates the required direct axis voltage and direct axis quadrature axis voltage that provides the firing signals to this converter to provide the required modulation to achieve the required reference point that is detected by dispatch. Next, I may mention that we have for the control loop for the voltage source converters, 2-level, 3-level, and also for the MMC we have an outer control loop and an inner control loop. The inner control loop basically consists of current control, right? Okay, so after providing the direct axis and current control and the quadrature axis control, we determine the error, and basically this is done through decoupling terms, and basically we calculate the direct axis voltage and the quadrature axis voltage. From there, a transformation. There's something they call Clark's transformation to achieve the required ABC equivalent. So basically, these are DC quantities, right? So we are converting from a DC quantity control. We basically do that to basically make the control much simpler. So that is why we do from AC to DC control transformation. So from here, we are able to convert to the AC transformation equivalent and provide the firing signal to the A phase, B phase, C phase of the converter. Next, let's talk about the operating state of half-bridge submodule, right? I've described all the components of the half-bridge submodule in the previous slide, right? Okay, then I've shown you how a typical half-bridge submodule looks like. We have two IGBTs, the top and the bottom, and this is the submodule capacitor that basically stores charges to basically achieve the required voltage to operate this IGBT thyristor. So, for the operating state, we have 4 operating states of this IGBT module, right? Okay, so the first one is when the IGBT 1 is on, the top one is on. So basically, current flows through the freewheeling diode to charge the capacitor, right? So basically, we have a positive polarity of the current flowing through the upper arm. So this is charging the submodule capacitor, right, to achieve the required submodule terminal voltage. The second state is discharging, right? And discharging, what does it mean? This is shown over here, right? So that is when the polarity of the arm current reverses to a negative. It's flowing in the opposite direction, right? So we are flowing from here and discharging, right? And we ask yourself, when does this occur? This occurs when there's a fault on the DC cable, right? So that is when you have the submodule capacitor discharging first to the faulted points, right? This occurs when during energization of the converter. So that is when the converter is getting charged. Next is the bypass state, right? Okay, so after a fault occurs, right, basically you have the fault flowing through after the cable has discharged, after the sub module has discharged. There's something they call bypass stage, where the cable discharges through these freewheeling diodes, right, to the faulted point, and bypasses the transistor itself. So it flows through this freewheeling diode to the faulted point and back. Then again, when basically the grid side steps in, then again it fits to this. Next is another bypass state, right, but with opposite polarity, right? Okay, so this is when it flows through here and bypasses the IGBT submodule. So now let's talk about the different fault characteristics of the half-bridge submodule, right? Okay, especially when you have a half-bridge submodule or a converter that is integrated to an offshore wind farms, and it has a DC transmission cable, right? So it has a converter on the offshore facility. It also has a converter on an onshore facility, and an onshore converter is integrated to the AC grid, right? Okay, so if you have a DC pole to ground fault on the DC section, let's say you have this is the DC section, this is the AC section of the converter. So if you have a DC pole to ground fault right over here, this is what is going to happen. You are only going to have two stages, right? So there's going to be abrupt, a little dip in the voltage level of the submodule capacitor, right? Just slight dip. So the voltage is going to dip a little bit. It's not going to lead to a full dip. No. Next is the DC cable is going to discharge, right? Remember, I may mention that the DC cable has a high insulation capacitance, right? So that is one of the requirements when you are energizing the HVDC scheme. You need power, you need reactive power to charge the DC cable, right? So when there's a fault, this DC cable has to discharge to the faulted point on the DC side where the fault occurs. So that is considered as stage 1. That is when the DC cable discharges to the faulted point. Then when the DC cable discharges through the freewheeling diode, when it completes that and the DC cable is fully discharged, the next stage that steps in, that is considered stage 2, is when the grid side, that is when the grid itself starts feeding. Remember, fault current always flows from the grid. It flows through the grid freewheeling diode through the faulted point until a steady state point is reached. Next is when a pole-to-pole fault occurs. When, on the contrary, when a pole-to-pole fault occurs, we have 3 stages, right? So when a pole-to-pole fault occurs, that is when you have a dead short between the positive pole and the negative pole, right? So the voltage is actually 0. That is when the capacitor fully discharges. The voltage drops to 0 and fully discharges to the faulted point. So that is considered as stage 1. When the capacitor, submodule capacitor, completes a full discharge, next stage is considered stage 2. That is when the DC cable also starts discharging through the freewheeling diode to the faulted point. When the DC cable completes its discharge, next is the grid side, that is the AC side that has a lot of short circuit current starts flowing through the freewheeling diode through the faulted point.